All right, we have a big one to do today, so let's get into it. We are looking at nuclear fission, um, nuclear fission reactions, including controlled and uncontrolled chain reactions, and we're going to look at how energy is produced in this type of reaction, and just talk a little bit about some of the applications of this too. So, first of all, what is fission? Fission is where you have one large atom and it splits into smaller pieces. So usually when we talk about fission, we talk a lot about uranium-238. Let's say uranium-238. Okay, and uranium-238 is a very, very large nucleus. It's not particularly stable. It can spontaneously split into two parts. That's pretty rare. Or it can be induced. If it absorbs a free neutron, then that's going to make it even more unstable and it will very readily split into two. Okay, so the parts that it splits into, there are lots of different combinations that it can split into. Let's say, just for the sake of argument, that it's um, splitting into strontium and xenon. So let's say strontium 95 and xenon 140. Okay, and as well as splitting into those, it will release three neutrons as well. Okay, so this is a fairly typical nuclear fission reaction. Yes, fusion is joining together, fission is splitting apart. So you can see a lot of small pieces have come off. It's like you have a big marble, you hit it with a hammer, splits into two big chunks, and there's a bunch of smaller chunks that come out as well. So we want to be able to analyze relationships representing conservation of mass and energy in these types of nuclear transmutations. So conservation of mass energy, that is the mass energy in the original uranium and the mass energy of the products. That needs to be conserved across time. So relationships, so we can look at this in terms of conservation of energy, we can look at it in terms of mass defect, binding energy, and E equals mc squared. So law of conservation of energy, energy before has to equal energy after. So the mass energy before has to equal the mass energy after. We know that mass is kind of like a type of energy. We can see that through Einstein's relationship, E equals mc squared. So we know that it's the mass energy that has to stay conserved. Mass defect. So this is an idea where if you look at how much mass is in the original uranium, compare that to the mass of the products, there's going to be a defect, missing mass. That missing mass has been converted into energy. It's not really missing. And this idea of the binding energy. So this is energy that it takes to energy that's stored in the bonds holding the nucleons together. And when those nucleons are split apart, the energy in the bonds is released, and that is the energy that we have. So I guess the bonds themselves have energy, and in a massive atom, that energy takes the form of mass. When it splits apart, the energy is no longer there as mass, instead it's heat and light and stuff. Okay, so let's analyze this by actually calculating what amount of energy is being produced here. So we have the atomic masses of each of these things, right? The atomic mass of the uranium-238 is 94.919388 atomic mass units. You do not need to memorize this. Any question that asks you about the atomic mass of these things, they would have to give you that, right? They can't just expect you to remember the atomic mass of every possible atom. Okay, the atomic mass, I'm not going to be able to fit all these for the other parts are 139.9216. 10. And you'll notice that these numbers are written to a very large number of decimal places, right? So this 94 was not for uranium. It was for the products. Product 1, product 2, 3 neutrons, uranium. was 238, of course, 238.050784 U. Okay, you'll notice that the atomic mass for uranium-238 is a number that's very close to 238. You'll notice that the atomic mass for 95 is close to 95. You'll notice that the atomic mass for 140 is close to 140. Okay, this all makes sense. One neutron should have the atomic mass of about 1. You might not be given that in the exam. Instead, you have to find that on your formula sheet. Mass of neutron. So they've got mass of neutron in kilograms. If they're being really annoying, they might give you some masses in atomic mass units, some in kilograms. You need to go down here to where you see atomic mass unit is equal to this number of kilograms. So you're going to have to convert to AMU in order to get it in the same units as these. Alternatively, you can convert all of these to kilograms using this same conversion factor here. Let's stick with AMU for now. 3 neutrons is going to be 3 times 1.008005 U. There we go. Okay, so we have this on one side. These 3, we need to add them up on the other side. So when they all add these 3 together, you get a value of 237.866993 U. They're added together. Okay, so let's think about this. We have this idea of conservation of energy, but we have 238 atomic mass units here and 237 atomic mass units here, 0.8. So really there's about a 0.2 difference between them. Yep. Mass defect. Yes, there is a mass defect. Some mass is missing. Again, about 0.2 atomic mass units. Binding energy. There was binding energy holding this uranium together, but now the binding energy is not holding the pieces together anymore. That binding energy has separated into some other form of energy. And Einstein's mass energy equivalence. Okay, E equals mc squared. Let's use that. So E equals mc squared to find out how much energy was in that binding energy, or how much energy is in that mass defect, however we want to look at it. M is going to be the mass defect. So I need to take 238.05, etc., minus 237.86, and I get something close to 0.2, like I said. I get 0.183791 U. Okay, now I just need to times that by c squared, and I get the amount of energy. Wrong, because this is in atomic mass units, and this equation is assuming that I'm putting in kilograms. Kilograms in here to give you joules over here. Okay, so we're going to have to look at our formula sheet. Let's think of a couple of ways to do this. There are a couple of ways. We can convert the AMUs to kilograms and then get an answer in joules. Or we can use our atomic mass units and get an answer in mega electron volts. That's another way to do it. So that's what I'm going to be doing now. This 931.5 mega electron volts to the speed of light squared. That is the conversion factor I'm going to use. So in order to do that, the amount of energy I have is going to be equal to mass, so 0.183791, yep, times the conversion factor, 931.5, is that what it was? Yep, 931.5. And so in the equation, it says times c squared here, but 931.5, you'll notice that that is divided by c squared, so those two cancel out, so that should give you your answer of 171.2 mega electron volts. Okay, that is the amount of energy released from one uranium-238 atom splitting in half. Now, it can split into different amounts of pieces, okay, which releases different amounts of binding energy. This is not what you will always get for uranium-238 splitting, but it is close. Usually something, if you have something close to 200 mega electron volts, that is pretty standard. It can be as low as, say, 150, as high as 250, but it's going to be somewhere in that ballpark for mega electron volts. And again, you've got enough conversions here to turn that just into plain electron volts. You can turn it into kilograms for mass defect. You can turn it into joules from electron volts to joules. You can do any of those conversions. Look at what the question is asking you to give your units in. All right. This is, as I said, a spontaneous decay. The uranium is just boop, splitting in half. However, the reason why this is so useful is we can induce fission. If a slow-moving neutron collides with uranium-238, turning it into uranium-239, which is unstable, it will then split very, very quickly. This can cause a chain reaction. So what you'll notice here is that it's releasing 3 neutrons. And if there are other uranium-238 atoms around, those 3 neutrons can go hit those uranium-238 atoms, induce fission, make them split. They release more neutrons. It's not always 3, could be 2, could be 3. I don't think I've heard of 1 or 4. Release more neutrons, which also go out and hit other uranium-238 atoms. This is called chain reaction, because one atom splitting releases neutrons, which trigger another atom splitting, which releases neutrons, which trigger another atom splitting. One triggers another, triggers another, triggers another. Like a line of dominoes, it's a chain reaction. They chain together. There are 2 types of chain reactions that we need to talk about, controlled and uncontrolled. Let's talk about the uncontrolled first. So you have a lot of uranium. A lot of uranium-238. Here they are. Here's all your uranium atoms. Some of them, for some reason, are a bit bigger than others. These are uranium-238s, right? So, one of them spontaneously split, and pew, 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 3 neutrons have come out of that split. Now, some of those neutrons might just dodge and miss, but some of them might collide with atoms like these 2. Okay, that causes those 2 to split. Pew, pew. Each of those will now release more neutrons. This one might release a couple, this one might release 3, and then out of those couple, some might miss, some might split atoms. Again, some might split atoms, they might all split atoms, which is going to release even more neutrons each, 2 or 3. Right? You'll notice we had 1 split, and then we had then we had 2 splits, and now we've got 4 splits. And from those 4 splits, we're going to get possibly 8 or more splits. It's going to exponentially increase, right? On our graph, it's going to look like 1 split first, then 2 splits, then 4 splits, then 8 splits, and it's just going to zoom up. This is an uncontrolled chain reaction because it gets exponentially bigger the more time goes on. And in my diagram here, I've got just maybe 20 atoms separated by a lot of space. But no, we're talking about a lump of uranium. It's a metal. There's going to be billions of atoms crammed into a very tiny amount of space. Okay, they're going to be triggering each other, right? Millions and millions of times in millions and millions of times in a short amount of time. This is how a nuclear bomb works. Okay, so what's a controlled chain reaction then? Controlled chain reaction is very, very similar. You still have all your uranium atoms. Let's say our starting one's over here. Okay. The uranium is split. It releases a bunch of neutrons. Now, let's say that 2 of these neutrons, this bottom one and this top one, were both on the path to hit new uranium atoms. To control a chain reaction, you just need to insert a new substance that will absorb the right proportion of neutrons so that some are absorbed, some will miss, and some will collide, splitting a new neutron. Okay? Again, this new neutron might produce this atom might produce some more new neutrons. Maybe a couple of them were on the right collision courses, but again, you have this material, It's going to absorb the right proportion of those neutrons so that only one will split. Okay, this is a chain reaction where one causes one to split, which causes one to split. And again, it's one causes one, causes one, causes one. Okay, because some of the extra neutrons are absorbed. Now, in a controlled chain reaction, I mean, technically, a controlled chain reaction could be one atom splitting one atom splitting one atom. But really, it's more of a probabilistic thing. It's more like you have a million atoms which are triggering about a million other atoms, triggering about a million atoms, rather than a million to 2 million to 4 million to 8 million and soon to a billion at once. Okay, as long as the numbers stay in the same proportion, the same number of atoms are splitting, over time. Okay, so really the difference is just between one of them being exponential and the other one staying, maybe the other one starts off a bit exponential, but then you put in your controls and then it hovers off and stays at a steady pace, right? Um, these black things could be made out of anything. You can use cadmium, I think is a common thing to use to absorb neutrons and this is what's used in a fission power plant, right? Uses nuclear fission, often uranium, to create electricity. The heat generated by this energy is used to boil water into steam. The steam turns a turbine. The turbine generates electricity. Um, if you want the rate of reaction to be higher, you just pull these control rods out a little bit more, let the number of reactions rise a bit, and then put them back in to keep them steady again. Nice and easy. If your reactions are going too fast, push them down further. It absorbs more neutrons, meaning less reactions are going to take place, and you can pull them out again to the right level to steady it out again. Okay, I think that's all we need to know. Goodbye.